Section 4.1 in our book, we're going to use the first and second derivatives to learn more about the graphs of y equals f of x. So I have here in yellow a very complicated looking function, and certain interesting points have been labeled. We'll talk about those more in a moment. On the right in the green, you can see our definition for what's known as a relative or local extrema. So the extrema is the generic term for either a relative maximum or a relative minimum. And some people and some authors and some books use local interchangeably. So I'm kind of a relative max and a relative min. That's the way I learned it and the way I've used it. But some people, you'll hear it referred to as local min and a local max as well. So our definition for a relative maximum says that f has a relative maximum at a point. That's one thing to be really clear on. In the world of AP, a relative maximum, relative minimum is always given as an ordered pair. So it's p comma f of p. If f of p is greater than or equal to f of x for all x in some open interval containing p, what that's saying is that the y value at that point is greater than or equal to the y values in a little region around it. So it can be a little mountain top, but it doesn't have to be the tallest mountain top in the whole range. It doesn't have to be the very largest point. It's just the largest in some little region. And the definition for relative minimum is the same, except you just switch it to a less than or equal to. So if the y value is less than or equal to the y values in some region around that, then then that ordered pair is a relative minimum. So let's look at this and see if we can identify at these points A, B, C, D, and so on along here, which ones are relative maxima and which ones are not. Now, the endpoint here is an interesting question, and different authors treat that differently. Some authors of some textbooks say that a relative minimum or relative maximum has to occur on the interior. It cannot be at an endpoint. Other authors say that it could be a relative minimum or a relative maximum. Because of that, they will never ask you on an AP exam if an endpoint is a relative min or relative max, because they know it's going to just depend on what textbook you ended up learning from. Our authors don't consider that to be a relative minimum or maximum, so we're not going to worry about it either way. So at B, you can see here that is not the largest in some region around there, so that is not going to be a relative maximum or minimum. Now here at C, you can see this is the largest y value in some region there, so that is going to be a relative maximum. At D, this is a lowest point, kind of a little valley there, so that is indeed going to be a relative minimum. At the point E, that is the tallest point in that little area, so that is a relative maximum. Now F is kind of an interesting question there. You can see that point right there is in fact the smallest region in that little area around F, so that is in fact a relative minimum. And likewise at G, we can see that this is a relative maximum because it's the largest y value of some little interval containing G. Now at H, there is no point on the curve there, so there isn't a relative maximum. And at J, now this is a really strange, this is kind of a trivia question. What I'm trying to do here is draw a little horizontal line segment. So this point right here, according to our definition, that it is the largest y value in some little region around there. Well, it is greater than or equal to the y values around there. So by our definition, there is a relative maximum at J. Curiously enough, it's also less than or equal to the y values around there, so it would also be considered a relative minimum. In fact, all of these points along this horizontal segment would all be relative minima and relative maxima. A very strange situation. And this point is not a relative minimum, nor is it a relative maximum. That's supposed to be a vertical tangent, but you can see it is not the largest nor the smallest of some open interval around there. Okay, so that was to clarify what we mean by a relative minimum and a relative maximum. Now, how do we find them? How can we use calculus to find a relative minimum or a maximum? Well, first we're going to talk about what we're going to call a critical point. If you look at these places where we had a relative minimum or relative maximum, you'll notice that, I'm trying to figure out what color to use here. Some of these came from a place where we had a horizontal tangent. That would be where the derivative is 0. Others came from either a corner point or a discontinuity, or it could have been a cusp as well. And so what we say is that we're going to define this idea of a critical point as a place where the derivative is either equal to 0 or is undefined. So that x value that makes the derivative of the function 0 or undefined is called a critical point. And we'll abbreviate that as a CP, because we'll talk about that a lot, and it just gets tiring to write out the word critical point all the time. Now, it's important to realize that a relative minimum or a maximum, and we generalize that, so a relative extreme point, or the plural of that is relative extrema, that includes both relative minimums and maximums. They will occur at a critical point, but not every critical point has to be a relative min or a relative max. This is an example of one where you're going to have a horizontal tangent here, but you can see it's not a relative min nor is it a relative max. This is going to qualify as a critical point because there's a vertical tangent there. The derivative is undefined, but it is not a relative minimum nor a relative maximum. Okay, so we get then, I'm going to scroll this a little bit, we get what we call the first derivative test for relative extrema, and this is going to be our bread and butter. We're going to use this a lot. So if x equals c is a critical point, that is, it's a place where the derivative is 0 or undefined, then if the derivative changes from negative to positive there, so imagine now we've got this point and the derivative goes from negative, that means the function was decreasing, to positive, that means the function was increasing, then that point c comma f of c is a relative minimum. If the derivative changes from positive to negative, that means it's going to go from increasing to decreasing, then we're going to have a relative maximum there. If the function does not, if the derivative does not change sign, then it is neither a relative minimum nor a relative maximum. Okay, now I'm just going to throw this out. This isn't a big deal, but we'll talk about this. It gives us some nice language to use. If the derivative was 0 there and it did not change sign, you can see the function was increasing, so the derivative was positive to left and positive to the right. Then a place where the derivative is 0 and it doesn't change sign, we're going to call that a shelf point. It just gives us a nice way of referring to it. Now, if the critical point came from a cusp or a corner or a vertical tangent or something like that, then that's not considered a shelf point. Only where we had a horizontal tangent, where the derivative was 0 and the function did not change from increasing to decreasing or decreasing to increasing. Just kind of nice to have words to talk about that. Okay, now we have what's known as the second derivative, and we can test that for concavity. So our book's definition, and different books define it differently, but our book says if the second derivative is positive on an interval, then we're going to say the function is concave up. And if the second derivative is negative, then we're going to say that the function is concave down. That's nice, and that's exactly how we're going to test for it. We're going to find the second derivative and see where that is positive or negative, and then we're going to determine whether it's concave up or concave down. Now, just for the record, other textbooks will say if f prime of x is increasing on an interval, then it's going to be concave up. So that's another way of talking about it being concave up or concave down. And likewise, if f prime of x is decreasing, then that would also be a way of talking about a function being concave down. Another way some books talk about it, which is an interesting way to think of it, we can see in here that this part of the curve is concave down, and the tangent lines there all lie above the curve. And some books actually define it that way, that a function is concave down when it lies below all of its tangent lines, and similarly that when the curve lies above all of its tangent lines on that interval, then the function is concave up on that interval. So sometimes it's nice to have those words, so I'll just kind of put them out there. Now, a place where the continuous function changes concavity is known as an inflection point. So this point right here would be known as an inflection point. And it's called an inflection point or a point of inflection. And it's always, I don't know why, but it's always abbreviated POI for point of inflection, even though I think we usually use the word inflection point. But people just don't use IP as an abbreviation. You'll see it almost always as POI. Okay, now we have this, and people struggle with this. I'm not really sure why. I think it makes good sense. There's, in addition to the first derivative test for relative extrema, remember that's where we find the critical points and then see if the derivative changes from positive to negative or negative to positive. We have a second derivative for relative extrema. We don't use this as often, but you still have to know it. If the derivative is equal to 0 at a point, and the second derivative is positive. So think about what that means. If you have a point where there's a horizontal tangent, that's what the first derivative is equal to 0 means, and the second derivative is positive means that must be concave up at that same point. That is going to make that point be a relative minimum. Likewise, if the derivative is 0, again, you're going to have a horizontal tangent, and you have that the second derivative is negative, the function is also concave down. Those two characteristics together make us have a relative maximum at that point. Now, if the first derivative is 0 and the second derivative is also 0, then we know nothing. It could be a relative min, it could be a relative max, it could be a shelf point. We just don't know, and the second derivative cannot distinguish. We're going to have to use the first derivative test. Let's just use the second derivative test a couple times because we don't do this as often and people struggle with it. So we're going to use our second derivative test. So first we're going to find the first derivative, and that's going to be 2x minus 2. We'll set that equal to 0 to solve and find our critical points. So we have a critical point at x equals 1. Now we're going to take the second derivative, and the second derivative is the derivative of 2x minus 2 is 2. Now the second derivative evaluated at 1, well, it's 2 because the second derivative is always 2. Since that is positive, that means the function is concave up at the same place where its derivative was 0, that it had a horizontal tangent. That means we're going to have a relative minimum at, and we said the point was 1, and we plug that into the original function always to get the y-coordinate, which is going to give us, I believe, 4. And so we're going to get a relative minimum at 1, 4. And on the second one, if we take g prime of x and get negative 2x, we set that equal to 0, and we're going to get x equals 0 is a critical point. We'll find the second derivative, which is negative 2, and as we saw before, the second derivative, no matter what, is negative 2. That is less than 0. Since that's negative, that means it's concave down. The first derivative was 0, meant we had a horizontal tangent. That means we're going to have a relative maximum at 0, and if we plug that into the original function, that's going to be at 0, 4. Okay, let's go to the next panel, and we're going to do an example where we're going to use all of this stuff. Okay, so here's our function, x cubed minus 9x squared minus 48x plus 52. And we have a bunch of things we're going to try to find here. Where is the function increasing and decreasing? Where are their relative extrema? And we have to justify our answers. Intervals, find intervals where it's concave up and concave down. Find inflection points and justify that answer. And then we're going to put it all together in a graph. So let's do the first derivative stuff first. We're going to find f prime of x. So that's going to be 3x squared minus 18x minus 48. We're going to set that equal to 0 to find our critical points. So I'm going to factor a 3 out of that and get x squared minus 6x. Let's see, what is that? 3 goes into there, is that 16 times. So we're going to try to factor that thing. And let's see, we're going to get x, and 16 I think is 8 and 2, so a minus 8 and a plus 2 will give us that minus 6x. So we're going to get 8 and negative 2. These are our critical points. Now, we're going to do our number line. This is going to be our routine here. We saw this a little bit before. We're going to put our critical points on there. I'm going to put solid dots on there because that will make this equal to 0. We're going to test the far left region. So if we plug in something like a negative 3, then we're going to get, this is always positive. A negative 3 minus 8 is negative. A negative 3 plus 2 is also negative, and the product of a positive, negative, and a negative is positive, so our derivative is going to be positive to the left of negative 2. I'm going to plug in a representative from the middle region, say 0, so we're still going to be positive for the 3, and 0 minus 8 is still negative, but 0 plus 2 is now positive, and that product is going to be negative. And if I plug in something bigger than 8, like say 9, everything's positive and we get a positive. So to answer our questions about intervals where f is increasing where the first derivative is positive, and remember we're going to include endpoints on increasing and decreasing. So I'm going to include the negative 2, and then we're also going to go from 8 to positive infinity. We'll include the 8, and we can never include the infinity. The function will be decreasing on the interval from negative 2 to 8. That's where our derivative was negative. Now, we will have relative extrema. We can see that at negative 2, the function goes from increasing to decreasing. So that's going to make negative 2, that's going to be a relative maximum, and I need to find the x-coordinate, so I have to plug that back in the original function. It's going to be a bit of a challenge here. So I have negative 2 cubed is negative 8. Negative 2 squared is positive 4 times negative 9 is negative 36. Negative 2 times negative 48 is a positive 96. And then we have a positive 52. Holy smokes. Let's see, 36 and 8 makes 44. Negative 44 and a positive 96 is going to be 52, I think. Does that sound right? 52 and 52 is going to be 104. So I think we get a relative maximum at negative 2, 104. Now the justification part goes something like this. To justify that a point is a relative maximum in the eyes of AP, you have to say that the derivative changed from positive to negative there. You cannot say the function changed from increasing to decreasing. In the eyes of AP, you're just, when you say the function changes from increasing to decreasing, you're just saying that's what happens at any relative maximum. That's not a justification for why there's a relative maximum at this particular point. So I'm going to say because f prime changes from positive to negative. Now, we can see that at 8, the derivative goes from negative to positive. So the function is going to go from decreasing to increasing. So that means we're going to get a relative minimum at 8, and I'm going to have to use my calculator here. I'm going to pause it and plug this in and see if you can get the same thing. So I'm getting negative 396. I hope you get the same thing. So now to justify this, like we did before, we're going to say this is a relative minimum because f prime changes from negative to positive there. Okay? Now we're ready to move on to what we can get from the second derivative. So we're going to find f double prime of x, and that's taking the derivative of our first derivative. Here's our first derivative. So we're going to get 6x minus 18. Now we're going to essentially do exactly what we did with the first derivative. We're going to repeat that with the second derivative. We're going to look for where that's equal to 0 or undefined. And so that's going to give us 6x is 18, so x equals 3. Now that is not called a critical point. It doesn't really have a great name. I've kind of called it, and I think other people have called it too, a PIP. That is, it is a potential inflection point. And I think that's generally understood, although it's not embraced like critical point is with that same universal acceptance. So we're going to now do with the second derivative a number line there as well, just like we did with the first derivative. You should label that. And 3, I'm kind of trying to line it up vertically with where our first derivative is. So at 3, that's where, and in fact, I'm not going to make that a solid dot because that's just going to be our dividing point, possibly, between a change in concavity. So if I plug something less than 3, like say 0, into our second derivative, we can see it's going to be negative to the left. If I plug in something bigger than 3, like say 4, then we can see that the second derivative is positive to the right. So we can say, to answer that question C, f is concave down on, it's always going to be an open interval for concavity from negative infinity to 3. We're not including the endpoint. F is concave up on the open interval from 3 to positive infinity. And we can see that there is an inflection point because there's a change in concavity, and 3 is a point. Our original function was continuous. So I'm going to pause here, and again, I'm going to use my calculator to evaluate this at 3. Okay, well, I got a negative 146 for the y-coordinate there. And this is our inflection point, and our justification is going to have to sound a lot like what we did for our justification for our relative min or relative max. So this is a point of inflection because, now there's actually a couple ways we can do this, because I'm going to say f double prime changes sign there. It doesn't matter if it goes from positive to negative or negative to positive. It's still going to be an inflection point. Now, sometimes questions come up on AP exam questions where you might not actually compute the second derivative, but you can know from other information given that the derivative changes from increasing to decreasing or decreasing to increasing. That can also be a justification for an inflection point. But it's not okay to say it's an inflection point because the function changes concavity there. That again goes to that issue of, in the eyes of the AP, that is just a definition of what any inflection point is, not that particular one. Okay, let's see if we can put this all together into a big graph. I'm going to have to scale this pretty wonky because I've got some huge numbers here. But let's see what we can do. So we know we have a relative, what do we know? A relative maximum at -2, 104. So I'm going to call that 104 right there. And we have a relative minimum at 8, -396. So I'm going to say that's 8. And I'm going to extend that maybe a little bit longer there. And my scaling's not great here, but I'm going to call this -396. So that's going to be our relative minimum, and this is our relative maximum. Our inflection point is going to be at 3, -146. So I'm going to say right there is 3, and I'm going to say somewhere in there is the -146. Okay, now we can connect this, and we're seeing that, I'm going to slide this down a little bit, we can see that our first derivative is positive to the left of -2, and our second derivative is negative, so it's going to be increasing and concave down until we get to that relative maximum. Then we can see it's going to be decreasing here, but it's going to remain concave down until we get to that inflection point. So it's decreasing and concave down until we get to that point. Now it's going to continue decreasing till 8, but now it's switching to concave up. So it's going to decrease but be concave up, and then it's going to increase and be concave up the rest of the way. So it's going to look like that kind of classic cubic shape. All right, very good.